Okay, good morning, everybody. It's a pleasure to be here. I would like to thank Alesh and the organizers for inviting me. I'm also happy to give it. It's the first time I give a talk after such a nice opening as we had, another form of kind of natural language. I'm afraid I'm not sure I'll be able to be entertaining as the previous session, but I'll do my best. So the topic of my talk is titled Natural Language Knowledge Graphs. And as you will see along the talk, it's an attempt to try and bridge or between the perspectives of knowledge representation, as today might be most popular in the notion of knowledge graphs, to representing information that is given, that is available in natural language. And as mentioned here, it's joint work with a large group. Most people here are from Bar-Ilan. We also have a strong collaboration with a group from Darmstadt of Irina Gurevich. We have a joint project that's also progressing along these lines. The work is still in progress, so it's the first time I give kind of an official talk about this topic. And as you will see, we are still at the stage of formalizing this framework and building the first data sets, but there's already an interesting story, so I chose to talk about this topic, which is my main research focus these days. So let's start. To give a perspective, and by the way, am I heard fine at the end? It's okay? Yeah. To give a perspective, let's just remind ourselves, or for those who are not familiar with this notion, what are knowledge graphs? So basically, knowledge graphs can be seen as a relatively more recent term from the last few years, following the themes of semantic networks already in the 80s and paradigms in semantic web. It's a structured way to capture knowledge. So let's start with an example, and then I have a slide. Following slides just gives a few highlights of this framework. But you see here a snapshot from the Freebase knowledge base, maybe the most famous one. Freebase was a public initiative, and a couple years ago was acquired by Google. So Freebase as such is not available anymore. The data was transferred to Wikidata, and within Google, Freebase was the basis of the Google Knowledge Graph, which is a proprietary knowledge graph that is now used in many of their products, as well as in the search. So a fragment of a knowledge graph, as you see, it's kind of built around entities. You see Barack Obama, Honolulu, United States, etc., where edges represent relations between entities. So real-world entity, Barack Obama, place of birth, Honolulu, date of birth, a certain date of birth, profession linked to the concept of politician. As you can see, entities can be also general concepts, not just concrete real-world entities. And since relations are edges by nature of a graph, they are binary relations. If you want a more complex relation, you can have these kind of dummy nodes like event 8 about the marriage, describing the marriage relationship between Barack and Michelle Obama. So it gives both of them, but also the date, might have a location, etc. Okay? So these are typical knowledge graphs, or typical ways in which knowledge, human knowledge, facts are encoded in a structured manner. Okay? So the idea is to encode selected facts, selected types of facts that are considered to be prominent or important. And they are encoded as propositions, basically, similar, if you can think of it as kind of a first-order style logic interpretation. You have a predicate, you have arguments, they assert propositions by asserting predicates over arguments. The advantage of representing information in such a knowledge graph that it's structured, it's a well-understood structure, it allows structured presentation, you can query, particularly you can consolidate information, so you may ask in which cities lived spouses of presidents. Okay, so you can go through the graph and answer such queries, which are hard, of course, to answer in today's natural language question answering technology. An important point in such structured knowledge graphs is the relations and the entities are pre-specified. So it's pretty much kind of a formal knowledge representation language. You have to define these sets of contained by, place of birth, spouse, place lived, etc. All these has to be predefined. Okay? So that's the common story about, the highlights of the story about structured knowledge representation. Now, our motivation is, can we think of something that would be a natural language-based knowledge graph? Can we try and do something similar to capture the knowledge that is embodied in texts? Okay, so in text we have unbounded information. We know that it doesn't work by pre-specifying any type of relationship that might be expressed in texts. So we would like both to find a more kind of an open representation language that will enable us both to encode the knowledge as well as to communicate it effectively to others. So you may want to have an application that shows us what is the knowledge or the information encoded or expressed in a set of texts. So in this talk, I will, and I see there is, in this talk, I will basically define the notion of natural language knowledge graphs that we've come up with. And during that, you'll also see how such knowledge graphs can be annotated. So, of course, if you want to investigate some task, some new concept in natural language processing, you have to be able to set up gold standard data sets. So I'll show together both the definition of the graphs and the way people can create those graphs, gold standard graphs, manually, so we can start working on that. And I will illustrate the application potential. I will not talk about algorithms, okay? So let's start to give a bit more concrete setting, which is also kind of the scope of where we are with the formalization. I'll describe the first data set we are working on, and this is data set of event tweets. So when there is some news event, in Twitter you have feeds of many tweets that look, you'll see in a minute, like news headlines. So it's not the Twitter social language, but it looks more like, breaking news headlines, okay? But Twitter is a good source for that, because that's today where you get most of them, and it's an important source because people that need to track events like security, police, security forces, or if it's a financial event, finance people, try to follow these streams. From a natural language perspective, as you'll see, we will not encode at the scope of this presentation information from complete documents, even though we are actually progressing in that perspective, but these are standalone sentences, okay? So we don't have the phenomena of discourse within a document, just encoding headlines. So let's see how this looks like. This is an example of an event tweet. We use some available data set that has event tweets, clusters of event tweets. You can see there is some stream, and I'd like to understand what's going on, okay? So you can try reading and figuring out what's going on. That's what people can do today. If you start reading carefully, you see that there are different facts described in these tweets, right? There is talking about some plane from Russia. This plane was grounded by the Turkish military, was forced to land. This plane was carrying munitions, which probably the reason it was a passenger plane, but was carrying munitions, so it's the reason why it was grounded, and so on and so forth. So you have probably several dozens of facts in this stream of tweets. But it's hard to get hold of these facts unless you start reading and tracking what's going on. So what's the difference between this kind of textual representation of information and the knowledge graph we've seen a few slides ago? One might identify two prominent characteristics of knowledge representation or information representation in natural language text. Two dominant phenomena that we'll have to confront with. So the first is redundancy, right? So you have this set of tweets, or you have a cluster of 100 news articles about a certain topic. There is redundancy, right? The fact that this plane was carrying munitions or ammunitions is mentioned a few times, right? You have to trace that and understand that it's all the same fact. On the other hand, we have some also complementary scattered information, right? Because like this one said it was carrying munition, this sentence adds that it was from Russia to Syria, another one adds that it was for the Syrian government, right? Maybe it could have been for the rebels. So while there is redundancy and the same information gets repeated, there's also some complementary information referring to the same fact, but that is scattered. So somehow we would like to put things nicely together in some analogy to what's going on in a knowledge graph, right? When you put information into freebase, each fact will be just represented once. It will not be any redundancy, and all the arguments of a certain facts, like all the all the information about Obama's marriage, will be all expressed in the same proposition. But in text, we don't have that. So if you want to build some coherent knowledge representation framework for text, we somehow have to confront and somehow merge this redundant information while taking, in a sense, the union of complementary information. So that's what we would like to do. Okay. And then just to, I apologize, it seems that when it was switched to, I'm using Google Slides, so maybe that's not mature enough technology. And when it's projected from this computer, I see that there's some overflow in the headlines, but we'll manage with that. So you could imagine that if we would succeed to put all the information from all these tweets in one coherent graph, maybe we can put up, just as an illustrating application, to start with, some nice view, right, that just gives you the main facts. Looks like initially like a summary, but we don't want just to encode the summary. We want to track all the information, so you can click down into the details. So you click on Turkey, and you'll get Turkish military, and it's an anti-aircraft unit because some tweets gave this additional information in a scattered manner, but if we put it back together, we can look at it nicely. And a couple tweets maybe mentioned it was an F-16. The interception was also described as forcing to land, as grounding. Maybe it gives us better understanding of what the event was. The plane was a passenger plane, which was the exception here, that a passenger plane was grounded. And some tweets mentioned it was a jet plane, if we really want to drill down into the deep information. Okay? And you can figure out, we could drill down everywhere. So if you will have a nice graph structure that consolidates all the information from all this long stream of tweets, we could possibly present it to people in a much nicer way. And actually, this is kind of an illustrating example, but actually this is, for us, it's also one of the major driving applications. So I personally believe that this is the flavor of the next step, the next generation in information search or in knowledge search. If we're not just up to finding a single fact or a single website, but we want to search for knowledge in a certain domain, richer knowledge, richer information, I believe that we will move on to application like this one, interactive exploration of content based on appropriate representations, versus the flat, right? Today, I can just look at this sequence of tweets, or if I search for documents, I will see the flat list of Google results, and I'll have to read one after the other in order to grasp information. So it's not just an illustration. I believe this is also a very important driving motivation for this paradigm. Okay. So now we want to build this graph, something that will merge the information in a coherent way. Now, the way, before I describe how we propose to do that, I should say that we defined a structure that in order to create it, we almost didn't invent any new component NLP tasks. Okay, what we will show is that by taking some tasks that are already known in the NLP community, some of them need to be extended, and some of them maybe don't work that well. But still, by picking notions and tasks in the NLP literature, in the NLP community, that have already been identified, and putting them together in the way that I will describe, we can come up with a proposal for how the structure of such graphs may look like, okay? So first, I'm going to describe those, as a background, those existing component tasks that are already out there that seem to be relevant, and then I'll show how we put things together and extend it in certain points in order to define such graphs. Okay, so let's first look at the background. So if we start by looking at how we represent the information, the facts in a single sentence, the most common way is to look at predicate argument structures, right? It's in, for instance, this is an example of the University of Illinois Urbana-Champaign, Dan Roth group. That's their demo of semantic role labeling. I assume most of the audience is familiar with this task. So in semantic role labeling, basically you identify the predicates in the sentence and their arguments. And in traditional semantic role labeling, each argument has a certain role. So if we look here at the, so this is a sentence. If you look here at the arrival event, it has Danny as a subject, which has the role of the person that is in motion or comer, the destination to the restaurant, and maybe the purpose or some complement to meet Sarah. And we have also another predicate, meet, and the achiever of this meeting or the agent is Danny, and the goal is Sarah. Okay, so this is people, I know that TSD is mixture from different communities, people not familiar with semantic role labeling. That's basically the task. Within a sentence, identify the predicates, and for each predicate, identify the arguments and the role. Now, there is a recent variant of the SRL paradigm which came up last year from the group of Luc Zettelmoyer and University of Washington. At first also is Luheng He. It is called QA-SRL, question answering SRL. So that's a variant on the SRL paradigm, and the main point there is that the roles, instead of being a predefined set of roles like in PropBank or FrameNet, people familiar with these prominent semantic role labeling paradigms, instead of that, in QA-SRL, the roles are simply questions. So the role of Danny will be who arrived, or the role of Danny for the verb meet will be who met someone. Okay, so it's natural language questions. Each argument answers the question, right? Maybe a common way to view predicate argument structure is to say that each argument answers some question about the predicate. So in QA-SRL, these natural language questions are the roles. So it just means the only thing that we will take from that, because I'm saying that because we will use the QA-SRL paradigm for annotating in our schema, is that roles don't have to be predefined. They're open in the sense that whenever you have an argument, it answers some questions. So you just identify that there is an argument by identifying that here is a component in the question, in the sentence, that answers a question about the predicate. Okay, so just an open way to define predicate argument structure. That's what we need. Now, a variant of representing such predicate argument structures is the open information extraction paradigm, which basically is interested in extracting tuples, predicate argument tuples, of the predicate and the argument, more like in first order logic type of format. So we have here, Danny arrived at restaurant to meet Sarah, where arrived is the predicate, or Danny meets Sarah, where meet is the predicate. You see, it's pretty much the same information, and we actually have a forthcoming paper showing that from a QA-SRL dataset, you can derive OpenAI extractions. So it's just two different ways to look at the information. If you want the perspective, the point of view, even though they're equivalent, the perspective of OpenAI, that you want to isolate the individual facts. And again, we will follow this paradigm, because when you want to merge information, you somehow want to break each tweet or each sentence to the atomic facts, and then see how these merge, right? If you think about it, each sentence couples together different facts, and it's more of a choice of the author which facts to tie in the same sentence. You let two people describe a certain event, they will break the facts into sentences in different ways. So if you want to merge things and put things together, like in a knowledge graph, we want to isolate the facts. So we will do it by just following kind of something like the OpenAI representation, where each predicate and arguments will be put in isolation as an independent fact. Okay? So this is how we represent a single sentence. We cannot skip. I mean, there is a recent AMR, augmented meaning representation, which basically follows the previous notions, but puts a graph structure for an individual sentence. I'm just mentioning it for completeness. but it still deals with a single sentence. Now, it's interesting to see also what was done. So the previous representations were used to just capture the facts in a single standalone sentence. Now let's see what was done in the past in NLP to try and bridge information across different sentences or across different documents. So one line of such consolidation or aggregation of information has been done in the classical information extraction paradigm, what we may confront with OpenIE, we can say that the classical approach is closed IE. So in the closed information extraction paradigm, people try to extract information about predefined types of information. Okay, so the most recent one, maybe the most prominent paradigm these days is ERE. It's an ongoing kind of effort in the US, a large project there. Entities, relations, and events. And they define 5 entity types. You see here 20 relation types, 38 event types. And for these predefined relation and event types, for these predefined types of facts, they define a scheme how to extract information about, let's say, a certain event from multiple documents. And then they actually annotate coreference. So if I have 2 mentions of this flight, they will, in their gold standard, in the ERE gold standard, and suppose flight was one of the relations, one of the events, then in the gold standard and in the systems, they do try to do what is called event coreference to identify that this flight and this flight is the same event. And then when they fill the template of, let's say, where the flight is from, what's the destination, they will merge information from different places in the text that co-refer to the same flight. Okay? So they do this kind of consolidation, but only for a very limited set of types of information. Now, with respect to kind of open bridging of information, there is another quite small thread, research thread in NLP on cross-document predicate-argument alignment. And there are some works here, and the data set, maybe the most famous data set is called ECB. There is ECB, ECB plus, extended ECB, various extensions of the data set. And basically what they try to do, they take many documents in which certain events were mentioned or described in different places in the corpus. And they try to identify alignments like that, right? You see here 3 different sentences taken from different documents, all mentioning the same event of Lindsay Lohan checking into a rehab facility. Okay, so they'll try to make the event coreference. You see that this checked into refers to the same event as entered, refers to the same event as this checked into. That the yellow ones are the subject of this in this event, and this is the name of the facility. So they'll basically do these alignments that express these in colors, and also the predicate argument relations in each occurrence. So this is like drawing these alignments or coreference links between full events, but not doing anything, not merging them yet. But it's a step in the directions we are interested in. Okay? So we are going to follow all these approaches. The last type of existing inference that is very common and actually is used to merge information, and we are going to use as well, is coreference-based inference. Right? So if we have something like, I saw a boy, he was running, I can infer from that, from this text, that a boy was running, right? Because the he co-refers to boy, right? So for instance, if there would be this text and there would be a question, who was running, we expect the question answering system to answer the boy, not he, right? Because he is kind of not well defined, out of context. So this kind of coreference-based substitution, where if you have a coreference chain, every assertion applied on one element in the chain, right? The running was expressed about he, but since he co-refers to boy, the running applies also to boy, right? This kind of very intuitive inference, which is based on coreference, is often implemented in question answering system, in textual entailment system, and in many other applications. But it hasn't been formalized that much. It's just a technique that people use in many systems, at least to a certain degree. And within formal semantics, actually, DRT, discourse representation theory, originated by Hans Kamp, also does this type of thing. So in logical way, they would say that, let's say, X will be the boy, Y will be the he, and they will have an equation X equal Y to represent the coreference. And then everything that applies to X also applies to Y. So we also see this type of coreference-based substitution inference also in formal semantics. Okay? So these are various attempts, as you've seen, to represent information in single sentences and to somehow tie information to a certain degree across sentences. But there is no, like we have semantic role labeling or AMR for a single sentence. We don't have a unifying paradigm. How can we represent predicate argument structures for sets of sentences, for all this set of tweets about the Syrian plane? Okay? And that's what we'll try to do now. So our position is basically to rely on such extractions and coreference. And the novelty in what we propose is, one thing is, just as an overview, to suggest how exactly to merge these many different predicate argument structures based on the coreferences. And the other is also how to trace redundancies, right? If you merge all the information, there's a lot of redundancy. Like one sentence would say maybe that the jet was carrying munition, and the other would be that the plane was carrying munition. There is some overlap in the information in these two sentences. We somehow want to model and trace it. And we'll do that through entailment relations. If people that heard about my work know that we've been working a lot on textual entailment. We actually initiated this paradigm, and it's going to be embedded here in order to model the information overlaps between different sentences. Okay. So now, before I'll propose the structure of our graphs, I think it's important to first define the scope of this type of graphs that you want to have, okay? And to specify some requirements, because people may come up with some representation that looks sensible, but then if you don't agree on certain requirements or expectations from this structure, from this formalism, you might, at different decision points, you might decide to do it this way, to do it that way, and it's not clear which one is better. If you specify some kind of well-defined scope and certain requirements you want to meet, then it's easier later to agree on how this should be done and whether a certain way to do it satisfies these goals. Okay, so I have 3 slides about the goals, and then we can drill into the structure itself. And I think generally it's a good methodology. It's not always followed. People often just define some frameworks, but the goals and the requirements are not always well defined. So with respect to the setting, we will assume here that we represent information similar to open information extraction by natural language proposition. And what do I mean by natural language proposition? So a proposition is a predicate and a tuple of a predicate and arguments to which it is applied. But in natural language propositions, all these elements, both the predicate and the arguments, are natural language phrases or expressions. Okay? So in that sense, it is an open approach similar to the OpenIE paradigm. Okay? So these are a natural language predicate plus a tuple of natural language arguments that together constitutes a natural language proposition. Okay? Now, which propositions do we want to represent? So we will stick to what I call here verbatim propositions. So I'll only use, there is a typo here. I've only used lexical elements that were mentioned in the original texts. Okay? So for instance, if there will be a sentence about John eating an apple, one could say, okay, this text basically expresses also the proposition that John was eating a fruit, right? Because you can infer from a set of texts, you can infer more natural language propositions using additional lexical elements. But we will keep this as a separate layer, okay? We will aim at this point to represent in our graphs only proposition composed of the lexical elements that appeared in the fruit. So if John ate an apple, we'll only encode the fact that John ate an apple. While if you want to make further inferences, we regard this as a separate layer. So the graph will encode the verbatim information in the text, while we assume that there should be another inference layer that could do further inferences. And the reason to make this decision, it seems very natural because such lexical inferences are open-ended. So if you say, okay, I want my graph to encode all possible lexical inferences over these texts, it's really open-ended, and it seems quite hopeless to do that. If you leave this to another layer, you know, then you have some inference engine that will later perform whichever inferences that engine will be able to perform. But the graph itself will encode the original information in the text. Okay, so don't look for fruit if only apple was mentioned in the text. Now, we still want to capture more than the concrete propositions expressed in the text. So if one text said, let's say that the plane landed in Ankara, and another said that it was a Syrian jet, we'd like to be able also to infer that a jet landed in Ankara, right? Because we do want to merge the information. So the kind of inference that will yield new propositions that were not verbatim in any of the original sentences are exactly these co-reference-based information. Okay, a plane from Russia plus a Syrian jet will also represent the proposition that there was a jet from Russia, okay, which did not occur in verbatim in any of the original sentences. That's exactly this co-reference substitution that we mentioned before. And another type of merging that we would like to express is also based on predicate co-reference. So if we have the plane flew from London plus the plane flew to Paris, and we identify the co-reference that it's the same flight, we can infer the plane flew from London to Paris, right? So this merging or union, taking the union of arguments that appeared in different sentences, is also something we can infer. It's still verbatim, but it's new sentences, new propositions that did not occur in any of the particular original sentences. So this is the inference that will allow us to infer new propositions based on co-reference, but we will not make lexical inferences, okay? So this is going to be the scope covered in our graph. And once we want to cover this kind of the verbatim information, but merged through co-reference, basically we'd like to represent all the propositions conveyed jointly, right? So if I let you read 10 tweets, and by reading these 20 tweets together, you can formalize a new sentence based on verbatim and co-reference-based inference. I want that to be in the graph, so I want the graph to be complete. And of course, I want it to be sound. So if from my graph I can read various propositions, I don't want to read propositions that are not expressed by the original text, right? I don't want by mistake to create new combinations that are not valid. So that's my redundancy, my requirements. And I would also like, of course, a very a very technical requirement. I would like to trace the original mentions. So if there is a Syrian jet, I want to be able to know, okay, where are the original tweets? Which are the original tweets that told me that this was a jet? And I also would like to do redundancy modeling. Again, sorry that it's screwed a bit, but redundancy modeling, as mentioned before, I would like to model the jet and plane have some overlapping information. Okay? Okay. So let's see now how these graphs, how we propose to construct these graphs. And basically, we'll do two things. One is to consolidate the entities and propositions based on co-reference. This is just an overview. And the second, as mentioned before, we'll model the redundancy through entailments. So what are entities? Starting with an entity mention, what is a mention of an entity? That's the common notion in entity detection. It's a known task. You know, every kind of word or term in the text that refers to a concrete object or concept in the world will be an entity. Okay, the typical notion of entity detection, not just for named entities, but generalized for any type of concept or object referred by the language. Then what is an entity, right? We want to represent knowledge, some facts about the real world. An entity in this framework becomes simply a co-reference chain of entity mentions, right? If we have the jet here and the plane here, and maybe in another place it says it was a Boeing 737, all these will be a co-reference chain. And the fact that it is a co-reference chain states that all these mentions refer to the same real-world object. If you're familiar with the co-reference resolution task in NLP, the traditional task, when do annotators have to say that these three mentions co-refer? They are instructed to say, put these as co-referring if they all refer to the same real-world object. That's a standard definition of co-reference, okay? So what we need to take from this existing kind of prior art is the fact that actually each co-reference chain corresponds to one real-world object, okay? We don't necessarily want to look for Wikipedia. We want an open paradigm. So any object referred in the discourse will be expressed in the discourse by a co-reference chain. So each co-reference chain becomes an entity, an entity representing some real-world object, okay? And it means, for instance, just to illustrate, if we have these three sentences, you know, this is a co-reference chain about the jet, so we have one entity, E1, which the terms describing it are plane and jet. E2 is the ammunition, having two terms referring to it. Ankara is another, E3, one term referring to it, etc., okay? So each entity will be defined, each co-reference chain will be defined as a unique entity in our discourse, in the set of texts. And we will keep track of all the terms that were used to refer to that entity, okay? And of course, we'll also keep the track of the supporting, right, of the original mention. So we know that the plane was mentioned in these two tweets in these locations, and jet was like in the second tweet, in the second position, second word in the tweet. Okay, so we can keep track. Now we move on to propositions which are a bit more complex, but follow the same rationale. So what is a proposition mention? You know, like that the plane was carrying ammunition. That's a natural language proposition, right? Carrying is a predicate, plane and ammunition are the arguments. So a proposition mention is again a fragment in the text that describes a proposition. All this part in the sentence that says plane was carrying munition is a mention of this proposition about the plane carrying the munitions. And now what would be a proposition in this set of texts? You know, in the cluster of tweets. Again, it's a co-reference chain, right? If I identify that this carrying and this was transferring or this was importing ammunition, all these refer to the same carrying event, then the set of these proposition mentions is one real-world proposition, right? Is one fact in the real world described in my texts, okay? So let's see how these look like. It's a little bit more complex because propositions have a richer structure. So suppose we have first a single mention of this fact, right? Like plane carried ammunition from Moscow. We will represent it pretty much like in OpenIE or semantic row labeling, right? We'll just, it's convenient to represent it as a small graph, where two-level graph, where the predicate is the root, and here we'll have the natural language expression representing the predicate, and arguments as daughters. So let's see what we have here, right? The predicate itself, as you can see, we chose to represent the expression of the predicate as a template. If people are familiar with inference rules starting with the DIRT system, it's quite famous algorithm from 15 years ago, where we represent predicates something like that. So it's all the words involved in the predicate with placeholders, with slots or variables for the arguments. Okay, so X carried Y from Z. Okay, so that's how we present the predicate expression. And the arguments, as you can see, are the entities, right? Because at this point, we know already that this plane is E1 from the entity chains, right? From 2 slides ago. So we know that from the previous, we know that the argument, this plane, is E1. So whether it was plane or jet, we simply have to recall that E1 was mentioned in this sentence as the argument of carrying. And similarly, E2 is the second argument, and E7 Moscow is the third argument. Okay? And we will identify this as by these questions following QSRL paradigm. I won't spend time on that. Okay? And of course, we can keep track of the mentions, right? So each element in the graph, I know where it comes from originally. Okay? Okay. Now comes the second tweet, right? A second mention of the same fact. So I'm assuming already that when we did event coreference, we identified that this carrying and this carrying describes the same real-world event. Okay? Of course, we have to solve event coreference. It's not an easy task, but it's a known task. People have been working on it. That's what we need here. And of course, we'll need to improve the technology. So what will happen when we take the other one? What we'd like to merge into the same graph describing this particular proposition, all the information from both mentions. Okay? So basically, in the predicate no, we'll now say, yes, we have also another predicate expression used to describe this fact. In this case, it was similar, but it might have been saying transferring munition, right, etc. For the first argument, right, we see that in this occurrence, it's the jet. We need to align. We need to know that this jet and this plane are the same argument, okay? But notice that since we already know the jet is E1 just like plane, we don't have to change or to add anything here. The only thing we have to add is just adding another mention, right? We actually, at this point, we don't care whether the first sentence would say jet and the second plane or vice versa, right? When we merge the information, we know, yeah, it was an entity that could be referred either as jet or plane, and this entity was carrying the munition. An interesting thing happens here. Notice that the first sentence said that the plane was flying from Moscow. The second says it was flying from Russia, right? So now physically, the plane was taking off from exactly the same location, right, in some Moscow, one of the Moscow airports. But different sentences may describe an argument at different granularity levels, right? One says generally from Russia, another says more specifically from Moscow. Maybe a third tweet will say from which Moscow airport. Moscow has 4 airports, okay? So it means that when we track arguments, an argument may be expressed by different real-world entities, right? Moscow and Russia are different entities. In entity coreference, they don't co-refer. Moscow is one entity, Russia is another. But to describe this particular argument, both Russia and Moscow can be used, okay? So that's basically what we have here. I describe this incrementally, but what we do, we take the whole coreference chain and just collapse everything to a single graph, okay? So this is how we represent one proposition, a coreference chain of proposition mentions. Now there is a couple, I won't spend much time on that. There are a couple more complex cases you have to deal with propositions. One of them is that propositions can be embedded. For instance, here there is Turkey used military to force a plane to land in Ankara. So one proposition is the landing event, right? This sentence does tell me the proposition that the plane landed in Ankara. But this proposition is embedded also in another proposition, right, that it was forced to land in Ankara. So the landing event, right, was actually a proposition on its own, right? And that's the structure of natural language. We know that in natural language, a proposition, right, or a clause can be an argument of a dominating, of a governing clause, right? In this sense, the landing is an argument of the forcing. So we encode that as well. It's actually quite simple. It just says that in argument, instead of just having entities, you can also have another proposition as an argument, so you get a recursive structure. Okay, it's quite natural. In the SRL, basically, it's the same. Okay, so we can do that as well. And also, we may do implicit relations. Look at this Syrian jet. So we have here 2 entities, right? In the coreference chain step, we will identify that Syrian co-refers with Syria, right? Just in adjectival form, while jet co-refers with the plane, right? One is E1, one is E5. But the expression Syrian jet expresses some relationship between them, right? When you read Syrian jet, you understand that this jet had a Syrian identity or belongs to Syria, right? So there is a relation, but it's an implicit relation. This is also a known phenomenon in natural language. There have been semival tasks about it. When you have a noun compound, often it encodes some implicit relation. So all what we need to do is just to identify that it's an implicit relation. The belongs to is just some auxiliary annotation we collect during annotation, but auxiliary information, but it's not part of the graph. The graph would just have implicit here, okay? So just allow propositions in which the predicate is implicit, because the text doesn't tell us, but the text structure says there is some relation here between Syrian and jet. Okay, so we can keep track of these as well. Okay. So at this point, we can represent the entities and the propositions. Basically represent all the facts that were expressed jointly by the set of texts. But now if we start reading these graphs, right, for instance, this one, right, we can see that a plane was carrying ammunition, a jet was carrying ammunition. We can represent all these facts. But as I mentioned before, there is some redundancy here, and we want to model the redundancy or the overlap in information. And we propose to do that through entailment. So I'll skip the technical kind of definition, but basically what we'll do, within each entity, we will build a small graph of entailment relations and a small entailment graph. So if we know that the first entity can be described either as plane or jet, we would like to know that the term jet actually implies the term plane, right? If I said a jet landed, I can infer from that that a plane landed. So for instance, if I already communicated to the user was like in the application that I sketched earlier, if I already put there a jet landed in Ankara, there is no point to present to the user another sentence, a plane landed in Ankara, right? From jet landed in Ankara, I know that plane landed in Ankara. But for instance, if the tweet about the plane will come out first we'll have some tweet about plane landing in Ankara, and 5 minutes later, there will be a tweet about jet landing in Ankara. I know that I may communicate the fact that the jet landed in Ankara because it gives me new information, right? When we have an entailment relation, it's always from the specific, the more informative concept to the more general one. Okay, so if I track these entailment relations, these information containment relations, right? Jet entails plane means that the information in plane is contained in the information conveyed by jet. If I model these entailment relations, then I can keep track, which things have been which information has already been communicated and which information is new. Okay, this way you can track. If you remember what you presented to the user, you now know that you should only present new things that are not entailed by what you have presented already. Okay, that's the reason why you want to track these information redundancies through the tool of entailment. And we have that not just in entities, we have it in entities, we have the same for the predicates, right? If I know that a plane was grounded, I know it was intercepted, but not vice versa, because intercepting a plane may also mean shooting down the plane. Okay, so if initially there was a tweet about intercepting, and then there is a tweet about grounding, I do want to communicate the second tweet because it adds information. It says, yeah, this was just grounding, it was not really shooting down, okay? And similarly also for arguments, right? If I already reported about Turkish military, no point to report about Turkey, but vice versa, if I want to drill into more detail, I may start by just saying that Turkey intercepted the plane, but if the user will click down, I'll say the Turkish military, okay? So these entailment relations, these small entailment graphs enable me to track the redundancy in the information and to make sure that I can, for instance, present first general information, maybe I'll start by presenting Turkey and then drill down to the more specific to the entailing information, okay? So putting it all together, you can see that we get these graphs. We have one graph about each proposition. One proposition may be an argument of the other. And within each component, we also understand how much information relatively there is in each expression. And then I can choose, what kind of information I want to communicate, and I can track whether I'm going to communicate something that was already communicated, so there's no point in communicating it, okay? And of course, for each, so we have here the propositions, we have here the entities. Each entity is, of course, linked to all its mentions, right? It's just a pointer, and I can track the information. Okay, so to sum up, basically what we need to do in order to build these graphs is to put together a few existing known tasks, right? I have to do predicate argument extraction, similar to SRL or to OpenAI, okay? Then I have to identify the coreference chains. So when we build our gold standard, exactly our annotators annotate the predicate argument structures, like in QA-SRL. They mark coreference chains, just like in coreference data sets. And then we proposed a new way. The italics here means to say this is kind of the new part in the sense of suggesting how to put the information together in certain graphs. And finally, to track redundancies, we build these small entailment graphs. Again, entailment between lexical elements, already a task that in the domain of textual entailment, people have been working, also in my group, we've been working a lot on these problems, okay? So the novelty is really on how to put these things together. And by doing that, you can think of what we've done as kind of extending the single sentence semantic representations to a semantic representation of a complete set of text. How you can represent the predicate argument structure that is expressed jointly by a set of texts. Okay, it's moving from predicate argument structure of a single sentence to a predicate argument structure for a set of sentences or a set of texts. That's the step here. Maybe I'll skip this one. I mean, I'll just say the highlights. So you can see that we fulfill the requirements, right? We can represent all the different combinations of natural language propositions, and we can track the redundancies. I think we've seen that through the slides. Yeah. So with respect to application, so that's pretty much the structure that we are proposing. Just to mention a couple potential applications. I mean, the first one is what I mentioned already at the beginning, that I believe is likely. I believe that something of this sort is going to be the next step in information access for textual information, something like what I presented before in those illustrating slides of the application. You can see that based on these graphs, you can dynamically present information. Right in the graph, you know which propositions were most frequent, therefore most salient. By the entailment, you can decide at which granularity level, which level of detail you want to present the information. You can present things in a hierarchical manner. You can present things in incremental manner, thanks to these entailment relationships. And you can have this kind of exploration application that instead of just giving a flat summary that you need to read sentence by sentence, you can just dynamically see bullet style kind of headlines that enables you to go much more quickly and much more dynamically through the information. So this is, I think, maybe the most appealing application that can come up of these graphs. But it can also be used for standard summarization. If you build such a graph, it should be much easier to create an abstractive summary that just chooses parts of the information. And it can also be used for querying. If you want to ask some complex questions, that in order to answer them, you need to merge information from different tweets. You can use the graph for that. Or you combine, you can say, what do you know about this plane? And you can get all the propositions about this plane. So you can think of kind of semi-interactive, where you start with some query, but then you get to see all the information about it. And just to illustrate, you can even answer things like, if you want to know what happened between Turkey and Syria, you have here Syria and Turkey. You can search for all the paths in the graph between Turkey and Syria, and for instance, see that Turkey intercepted a plane, and this plane was carrying ammunition to Syria, right? Something that's quite hard to do based on, if you just give today's question answering systems such a question, given a set of tweets, they will not be able to answer it, okay? So we think that there is a large potential for these graphs. We also, just to give an illustration, our annotators use this tool in order to annotate all the predicates and all the entities and build up these coreference chains. So it's just that annotation tools that combine these tasks, these existing annotation tasks together. And also it allows you to draw these small entailment graphs. And once you just do all these standalone annotations, each of them of an existing task, the system can put things together and build a graph. We also have an initial visualization tool that shows all the propositions with the arguments, and here are all the entities. So after you have a complete graph, you can view it easily. And we're actually now moving to develop a prototype of this initial application. We collaborate with people from information science. We're going to perform user studies to see how such application can be more effectively used to explore textual content. So to conclude, I've presented an initial direction. There are many ways to extend it. For instance, we have only very initial treatment of contradictions, right? Maybe two tweets contradict each other. You would like to represent that as well. You want to model maybe some events, which there is a flight and there is landing. You may want to know that the landing is a sub-event of the flying. Right now, we represent it just as two separate events. We would like to add a layer eventually of non-verbatim inference, right? If John was eating an apple and John was eating a pear, maybe we do want to figure out that John was eating fruits and to present that as well as relations between different propositions. In our graph, each proposition has its own small graph. Maybe you want to draw some causality, temporal relations between propositions. So there are many ways to take many directions in which we can extend this to give you kind of a more complete knowledge representation paradigm. So to conclude, I was basically suggesting a consolidation framework. It models both the coreference-based inference and the information redundancy. And what we got is this kind of cross-text predicate argument representation. We believe it has many applications and many potential applications that I just mentioned. And at the bottom of this slide that was missing here was the thank you. Okay. I hope I left the designated time for questions.
Not much. So please, your questions.
Yes.
What about representation of contradictory or false information or subjective information? Say several words.
Yeah, right. So that's largely falling in this first bullet of future work. What we already have in our annotation tool, so one type of contradiction that is very natural to encode, and we start encoding as well, is when arguments contradict. For instance, maybe one tweet will say it landed in Ankara, and another would say it landed in Istanbul. And it's the same flight. You understand from the context of the tweet, suppose your co-reference system is good enough, you understand it's the same flight, so you understand it's contradicted information. You know, maybe there was some rumors, you know, some information is not certain yet. So both Ankara and Istanbul should be arguments of the landing event, right, of the landing proposition. So they will both be in the same argument bubble as we had Ankara and Turkey. But when you have, with Ankara and Turkey, Ankara was entailing Turkey, right? With Ankara and Istanbul, in that same argument, you'll draw a contradiction relation, which is very natural in the entailment setting, because entailment in general actually is a three-way task. When people do textual entailment, they say, does A entail B? Does A contradict B? Or there is no entailment relationship between them. Okay, so we want to start identifying contradictions at the argument level. But then you can imagine also drawing contradiction links between different propositions, just like you want to encode causality or temporal relations. So that's the general approach. And also for factuality, so both us and other people were doing work on factuality. So, you know, if you say the plane failed to land in Ankara, or didn't succeed to land in Ankara, then the landing in Ankara didn't happen. We need also to incorporate this kind of factuality information. So again, it's incorporating tasks that are already out there in the NLP community and has to be integrated. Yes?
No.
Sorry.
Please, very short question. We don't have much time.
Well, it's a similar question. The information found in social media, especially in tweets, often tends to be very vague and imprecise.
Short question.
Have you delved into ways to capture this, for example, using probabilistic or fuzzy knowledge graphs?
Right. So I mean, again, modeling credibility or certainty of sources is again a research area on its own. I think which can be and should be integrated here actually. Someone working in this area raised this question in a previous talk that I gave. Because we keep track of all these mentions, right, we can know on each fact from which tweets it came out. And in the metadata, you also know the source of the tweet. So if you have a module that models source credibility, you know, you can say, yeah, this fact was mentioned 10 times, and maybe you can plot the credibility or compute an average aggregated credibility score if you integrate a credibility assessment module. Okay, so I think the joint is that I think these graphs give you a very natural way to integrate all these technologies that address all the additional aspects that need to be addressed.
Come on.
How do you integrate natural language ambiguity? One sentence, 1,000 versions of interpretation. What do you do?
So again, that needs to be handled in the coreference chain. Like, for instance, I'll give you in the coreference change detection. And I'll give you actually a tough example, right? And that's I mean, this question, again, I'm saying it applies already to the traditional task of coreference resolution. Because, for instance, when we have Ankara, Ankara sometimes is used like landing in Ankara really designates a city. But sometimes Ankara is used as metonymy. I'm just giving even a tough example of ambiguity as metonymy for the Turkish government, right? Ankara threatened Syria, right? Blah, blah. You must put that in two different coreference chains. So again, you have to put in the best you can do in natural language disambiguation, and that will come in at the coreference chain resolution. Okay, just like when you do entity linking, right? When you do Jordan, you see Jordan, you have to know, and you do entity linking to Wikipedia, you have to know whether you should link it to the Jordan River, to Jordan Country, to Michael Jordan. Okay, so you must take these decisions when you build up in our framework the coreference chains. Okay, so do your best then, and you know, and that's where will be expressed. Again, of course, this is a long-term, right? I mean, people have been working on predicate argument structures for decades now, right? So this is a long-term goal to get NLP technology to the level that will be high precision in all these tasks will take time. But I would like to say, though, that I think because of the nature of redundant information, you see in these tweets, for instance, a lot of the tasks are actually easy. So we hardly found examples for negations or contradictions, okay? It may appear a little bit. Ambiguities, there are some, but many things are not ambiguous. So I think, like, if you start with a recall of 30% of the information, like if you manage to capture nicely, to summarize the 30% most salient facts in 500 tweets, it's already useful. So I'm saying, I think these things have the potential to be useful even while our performance is still mediocre. Because of this so much redundancy, things can become useful even before, you know, without waiting for NLP technology another decade to advance.
Did you think about applying to the scientific
Last
knowledge?
question.
So, can you just...
Say it again.
Applying to the scientific knowledge.
Yeah.
Is it possible, and maybe some modifications are required?
Yeah, it's a great question. In fact, the next domain in which we start collecting data is the educational domain. That's in this joint project with Irina Gurevich. So, like, suppose you have, it's a little bit, I think it has similarities like to the scientific one, of course. Just to give an example. So in the educational domain, you might ask a query about gifted children. You have a gifted child, and you know we want to say what the literature says about educating and managing gifted children. So you make a Google query, and you get 1,000 documents about gifted children. You want to take the most salient sentences and aggregate them. So there you'll find many things that are generics. Like, for instance, gifted children are not high achievers, are often not high achievers, right? More generic sentences. So you may have you may need to do some extensions to model generic information, or to model kind of rule-based, if something happens, then another thing happens that you find in scientific texts. Okay, so some extensions will be needed. I cannot say right now exactly which, but from the initial experience we had, we see because everything here is just based on predicate argument structure, eventually also scientific texts and generic texts, they express information through predicate argument structures. So I think there is good potential, but you know, it's still to be seen.
Okay, I thought more about X-archive.
Yeah, right, it's another domain. So I mean, we haven't looked at that, but I mean, it's to be investigated. I mean, that's a bit a step ahead.
So I'm sorry, but we have time schedule, so your time now is for coffee break.